Usually we have two sessions of exams in the same two exams in the same session. So two on February, March, then two on June, July, and then two on September, something like that. And we wanted to ask you what did you think about this? So if you put them in this way or in other ways. And someone was also asking if it was possible to make another exam during April by so out of the session.
Could you say it again? As I understand, there are several attempts to pass an exam, right? So one is during the winter at some moment, and also later, right?
So usually we have two times in winter prior, then two times in summer, and then two times in autumn. Something like that, right?
Two times you mean one? So one time is one written exam and one oral exam. Or,
yes, and then another time again written and oral. If we have written and oral, I didn't written. So we have written and oral. Yes. And yes, someone was asking if it was possible also to have an exam during April.
so let me think. I think I'll be interested in April. I think it's possible. But why is it like someone cannot attend exams during the winter, or someone is afraid that they will not pass the exam from the first attempt?
Yes, and I think that during this semester, some of us have many exams to do. So one may think that he could do one later, but it's not for everyone. Someone asked me this, and he's not here today, so I was doing this to just inform that someone might ask this.
So you want two exam sessions during the winter, then in April, and also in autumn, or when?
One extra for who like. But yes, we should have as a starting two during winter. So February, one in January, and one in February, or two in February, as you can.
And another two sessions like standard ones in which months? Is it in summer or in autumn?
One is in June, July,
Ah.
and then there is another in September.
I see. So I will think, but all people are in the mailing list, right? So I can ask this by email.
So you can tell us in the next days which will be the dates for winter.
Okay. Okay, so let us start a very short topic for which we know everything. So I would like to tell about the green function of the heat equation. On a circle, and also on the interval. And uh, and also on a torus. It is also doable. So so let us try to study the following simple problem. So we have a u of t and phi, and uh, uh, this u of t and phi should be periodic in phi. So u of t phi plus what plus plus 1 should equal to u of to u of t and phi, and so it's boundary condition, and this u should also satisfy the heat equation. Like dt of u should equal to dxx u. So how to solve this? We can say that our u can be expanded in Taylor series. Uh, 2 pi I and phi. Uh, and let us also say that we are looking for the gain function. So let us say that u of so there should be some initial condition. So let us say that it is an initial condition like for the gain function u of 0 and phi is equal to delta function of phi minus phi 0. So therefore, we can say that u n of 0 are equal to e to the minus I 2 pi I n phi 0. We check that this is an expansion of the delta function. So now what? Now we need to substitute this equation into the heat equation, this expansion into the heat equation, and write equations for un of t. So as before, we can say that dt u n of t equals to minus 2 pi I minus 2 pi n squared times un of t. So we conclude that un of t is so taking into account this initial condition, we conclude that un of t is e to the minus 2 pi I n phi 0 minus 2 pi n squared t. So so our u, maybe it is better to write it as to call it a green function, like But let us write this before. So u of t and phi, which is a gain function of t phi minus phi 0. This equals to sum over integer numbers. So there is such a formula, and so it is very similar to a function which we already had, but mm, so let me write uh, let me write some notation. So this is called set 3 of phi minus phi 0, and 2 no, 4 phi I t. Uh, the definition which we need is the following. So we had theta 1, which was sum over integers. Theta 1 of z and tau. Well, this one, and this one is theta 3 of z and tau. It is a sum over oh, this is n plus 1 half. So there are these two functions, and there are also other functions. So some mnemonic rule for this is the following. So we have this fundamental domain, which is 1 tau, and we have a function which has 0 at z equals 0. This is theta 1. Then there is some function which has 0 at 1 half. This is theta 2. And there is some function which has 0, so it is 1 half. And this is tau over 2. There is some function which has 0 at this point, 1 half plus tau over 2. It is theta 3. And there is some function which has 0 at tau over 2. This is theta 4. So, and looking at this picture, we can write some formulas. Like if you want a function which has 0 at 1 half, we should just remove this minus 1 to power n. In this case, when we substitute z equals to 1 half, it will precisely give this minus 1 to power n factor. So this is theta 1, and this is theta 2 of z and tau equals to sum And the remaining function z and tau is in this one. So they can actually be obtained from a single function using such half shifts by 1/2 and by a tau over 2. So there are these four Jacobi theta functions. On this theta 1 appeared for the Laplace equation, and theta 3 appears in a little bit different way for the heat equation. So, but in principle, the series is nice, but it is not very convenient for the limit when t goes to 0, because in this case, in principle, when t is 0, we can recover the formula for the delta function, but it would be nice to see what happens for small t. So in the continuous case, we could this sum corresponded to some Fourier transformation, which could be computed explicitly because it was Gaussian integral. And an analog of this procedure here is Poisson summation, which I already told at some moment, and now I would like to use it. Let us remind what it is. So if we say that there is some function of x, and there is some Fourier transformation of this function, which is equal to to the integral from minus infinity to plus infinity to the 2 pi I px f of x dx. Then sum over integer numbers of f of n is the same as sum over integer numbers of f tilde of n. Let us try to use it in our case. So this f of x in our case is e to the 2 pi I 2 pi I x phi minus phi 0 minus 4 pi square and x squared t. And let us compute this Fourier transformation. Integral from minus infinity to plus infinity e to the 2 pi I x minus phi 0 minus 4 pi squared x squared t squared plus pi I px dx. So we are computing f tilde of t. So it is squared t. Uh, so here it is t plus phi minus phi 0 dx. Mm. So this one should be correct, I think. So and this is Gaussian integral times exponential, and this Gaussian integral, it is square root of pi divided by square root of this. So it is 1 over square root of 4 pi t e to minus 1 over 4t phi minus phi 0 plus p squared. So if we take this take this answer and plug into the Poisson summation formula, we obtain that this gain function. Where? Which double product? Mm. Hmm? So, I see. Mm-hmm. No, but this one is correct, right? Mm-hmm. Yes, yes. Thank you. So. So if we now use this first order summation formula, then this grand function is a sum over integer with maybe p integer 1 over square root of 4 pi t e to uh, 1 over 4t pi minus phi 0 plus p squared. So the picture for this is absolutely clear. We can say that our functions on a circle are just periodic functions, and to pi periodic, and uh, uh, so the gain function, so we can think that this gain function is a kind of uh, a sum of gain functions corresponding to the infinite number of images of a single point. Okay, so we have some Gaussian peak at 0, then some peak at 2 pi, so it goes to 0, then another peak, then at 4 pi, and so on. So minus 2 pi. So it looks like a absolutely clear picture. So this is for sure periodic because we just took a sum over integer numbers. So it's periodic by construction, and it solves heat equation also because it's some solution on the infinite line. Mm. And if you now want to restrict to some segment, so if you now say that phi is from 0 to what? Maybe let us say that phi is from mm, okay. Oh, sorry. Actually, I missed some. Oh, it is not to pi periodic. It is integer periodic because it is uh, addition of the integer number. But and now imagine that we want to solve this problem uh, uh, on the interval. Like phi is from 0 to
Shouldn't be exactly the square
hmm?
the t shouldn't be outside the square
No, because it was just t, not t squared. The integral. Mhm. So let us now try it. So are there any questions about this? So we check the recording. So now we can try to solve another problem. Phi is from 0 to 1, and u of 0 equals u of t0 equals u of t1 equals to 0. So we want to maybe let us write it like for the grand function. G of t phi t0 phi 0 equals to t of t1, phi 0 equals to 0. So how to construct a solution of this equation? We can of course do it using this Fourier transform, but we can just guess it using this method of images. Namely, let us draw the following picture. So we have our interval from 0 to 1. And we have some point phi 0. So we should have some peak here. But if you want this function to be 0 at 0, we should add another such peak at minus phi 0. And so this is function from minus 1 to 1. And then we should just add the same pattern periodically. Like so it is 2, it is 3. So we should have something like this. And so on. So this way we get some function which is so the formula for this is the following. So g of t phi 0 equals to sum over so this is 2 periodic sum over an integer 1 over square root of 4 pi t e to the minus 1 over 4t for t phi minus phi 0 plus 2n squared minus sum over integers. Maybe if you want this to be analogous to the previous case, we can write here not 1 but 1/2 to have everything identical. So this is 1, this is 3/2 minus 1/2, and so here the sum will be over the integer numbers. So this equals to this again function on S1 of t phi minus phi 0 minus again function on S1 t of phi plus phi 0. And of course, if we ask for another boundary condition that phi derivative of g is 0 on the boundaries, we will have the same answer, but here we should put plus, and that's all. So it is absolutely analogous to gain functions of the wave equation of of Laplace equation. So this method of images works always. And also, if you want to compute this gain function on on some rectangular domain, this is also doable. In this case, we will of course have a summation over several integer numbers, and such objects are also known. They are called Riemann theta functions. So so, uh, as you see, there are some well-convergent series, so such formulas can be even practically useful. Mm. So, are there any questions about this? Also, we can notice, looking at this formula, that this Poisson summation turns some series which contained where is it? It is here. It turns some series which contains n squared times t to some series which essentially contains p squared divided by t. Or n squared divided by t. And this is called modular transformation. So, mm, like, this Poisson summation, it sends tau to -1 over tau. And there is another transformation which acts trivially. It is a shift of tau by 1. So it can only, I think, switch one theta function to another one, and that's all. So, these transformations are important. For example, people study functions on the upper half plane, which are differential forms of a certain weight, and in this transformation, they are called modular form. So, and uh, one maybe the first example of modular form which you can construct in this way is to take tau 1 prime of 0 and check that it it is multiplied by some power of t under this transformation. And so, and if you take I think fourth or maybe don't remember which precise power of it. Um, maybe 1/3. Yeah, yes, 1/3. It will be the Dedekind eta function. Mm. But so it's really a side remark here. So, so maybe that's all about Dedekind functions. Do you have any questions? Mm. Because I want to start the new topic. So the new topic is separation of variables. So you can study equations like a heat equation.
Before time, it seems to me that the tau is not to 1 over tau, not minus 1 over tau.
No, because tau is so in this case tau is purely imaginary, so that such series is convergent. So this transformation definitely maps purely imaginary with positive imaginary part to purely imaginary with positive imaginary part. So uh, or in other words, we can say that it maps a t to something like uh, um, pi over t, something like this. But a t is related to tau by multiplication by I. So, so it is really some map of the upper half plane to the upper half plane. Is yeah.
Because we can write the second part like plus en squared t. So
Mm,
is it,
we can put here I and here I. And
we can write the minus like t squared, and so
uh,
yeah,
and if you do this here, then uh, it will be I over 4IT. So and here there is also this minus sign. So, so is it fine? Mhm, mhm. Yeah. So uh, we can study, for example, heat equation or uh, so it can be dt, it can be dt for the wave equation. Uh, it can be just some number if you solve Helmholtz equation. But the idea in in all these cases is that if we live in the rectangular domains, so if x, y, z live inside the box, uh, then we can diagonalize this dx squared, dy squared, and dz squared operators simultaneously by something like a sine of uh, pi x over lx, uh, sine of pi y over ly, sine of pi z over lz. So, mm, so if we use such a basis of functions, namely perform such a Fourier transform, then these operators act by numbers, and we can reduce this equation to one-dimensional equation in time. But uh, uh, what about different domains? So, for example, what about circle and sphere? Uh, Disk and ball, to be precise. how to call this, like d2 or or d3. So we would like to have something like this also in this case. So and to understand what we can do here, we should switch to polar or spherical coordinates. Uh, so uh, let us start from polar coordinates. Uh, of course, the formulas are simple, like x equals to r cosine of phi, y equals to r sine of phi. And in principle, we can write Laplace operator on these coordinates just computing partial derivatives. But it is easier to do this using the action principle. For example, we know that wave equation utt minus uxx minus uyy follows from the action principle. Uh, so variation of the integral dt dx dy utt or ut squared minus gradient of u squared equals to 0. And if you want to write the Laplace operator in different coordinates, it is easier to write gradient in different coordinates. So, so suppose that we have some. Uh, so we want to ask what is a gradient of u in polar coordinates. Uh, we have some r, some radius vector r, and we can introduce uh, the unit vectors in r direction. We call it ER, and in the phi direction, we call this E phi. So they are orthogonal, and the length of ER is a length of E phi is 1. So gradient such a vector that its scalar product with any vector is equal to derivative of a function along this vector. So if we just look at this picture and see what happens when we change phi by delta phi, so we can write something like this, that delta u, well, it's can be confused with Laplacian. Let us write delta u and the small variation of coordinates r and phi equals to or maybe let me first write a formula which I want to prove. So gradient of u is equal to er du over dr plus e phi 1 over r du over d phi. Because when we when we change phi by delta phi, and the length of a vector corresponding to such a change is r times delta phi. So. No, do I need to explain this formula, or it is fine? Maybe, I don't know. So, if we have so this is called action. Delta S is equals to 0. So if you now use this formula, then the action can be written as S of u is integral over dt. Then we should write a measure in this polar coordinates. And this measure is r dr d phi. And the argument is utt minus this gradient urr, ut squared minus ur squared minus 1 over r squared u phi squared. Maybe we can put 1/2 here for the simplicity. Uh, and if you now compute a variation of this action, perform all this integration by parts, then I will find that delta S of u is equal to integral over dt r dr d phi. And here we have maybe let us write it better this way: dt dr d phi d phi. Here we have delta u uh, times r u t t minus delta u r u t t plus delta u r u r r r u r r derivative, because we had to integrate by parts once, but this object was multiplied by r. And and in the last part we have plus delta u 1 over r u phi phi. So equation which follows from this variation is the following. So we should divide everything by r, and it gives u t t minus 1 over r r u r r. Oh, it's not enough space here. So comparing this with the original wave equation, we conclude that Laplace operator in this polar coordinates can be written uh, as this expression. Oh, I forgot 1 over r here. So it is 1 over r dr acting on everything. Let us write Laplacian of u equals to dr of u of ru minus 1 over r squared due to u over d phi squared. So it is plus. So is this computation clear? So equivalently, you can just perform this change of variables and compute explicitly this x and y derivatives in terms of r and phi derivatives and verify this formula. But this is some simple explanation of how to get this. Uh, So maybe I don't know. Maybe I can try to explain this formula.
The last time, when we have RU in the parentheses, uh, no, yes,
Mhm.
R, right? So we,
But what the difference? It's multiplication of functions.
no,
Yes. Thank you. dr dru. Yes.
okay.
Thank you. Hmm. Oh, maybe uh, let us come back to this formula. I don't think well how to explain it better, but let me try to do this once again. So so characteristic property of a gradient is the following: that if we compute uh, u of x plus delta x uh, minus u of mm, minus u of x. It should equal when delta x goes to 0, it should equal to the scalar product of delta x times uh, delta x times a gradient of u. And if we consider this a case uh, with polar coordinates, then expansion of delta x uh, into a combination of ER and phi is the following. So delta x is uh, delta R E R plus delta plus R delta phi E phi. So uh, on one side, uh, because it is just we just compute. Uh, on one side, we know that a scalar product of this delta x with gradient of u. So left hand side of this expression is delta r du over dr plus delta phi du over d phi. It's on one side, and on the other side, it equals to a scalar product of this vector when the gradient of u, delta r e r plus delta phi e phi uh, plus r delta phi phi uh, times gradient of u. And if you and now we see that since this R component is proportional to delta U over delta R, it is just delta U over delta R. And here we should divide by R, so that the scalar product gives gives du over d phi. Maybe let us write that this equals when delta x goes to 0. Maybe. So, so this way we were able to compute Laplace operator in polar coordinates. But let us now do the same with spherical coordinates. And after this, we start to think about separation of variables. So, so, formulas are the following ones. So Z is r cosine of theta, Y is r sine of theta, sine of phi, uh, x equals to r sine theta and cosine of phi. So if I draw a picture, it looks like this. This is x, y, and z. Uh, Here we have some angle phi in this plane. Uh, so that projection of our point along the axis is at the angle phi. And here we have this, so this is right angle, and here we have angle theta. And here is the distance r. So here we want to do the same. We want to introduce introduce three orthogonal unit vectors like this one in the direction of radius er. This vector corresponds to a change in the radius when we keep theta and phi fixed. Another vector lies in this plane, and it corresponds to a change of the uh, angle theta, and we call it e theta. And the third vector corresponds to a change of angle phi with fixed theta and r, and it is orthogonal to them, and it's orthogonal to this plane. So orthogonal vector is sometimes denoted by cross. So it is pointed to the surface of the blackboard. So it is vector e phi. So if we now do the same, if we see what is the change of our coordinate, then we can find that delta x, small change is maybe, well, let us delta x. It equals to delta r er, because we just changed the position by some delta r. But if we change angle theta, the length of path will equal to the uh, uh, so if we change this angle phi, it will so the distance by which this point will be shifted will equal to phi times or to delta phi times sine of theta, and times e phi. So and the last term is for changing this angle theta. So in this case, we see that it is theta independent. It will always equal to delta theta times oh, so I forgot to multiply by r here, r sine of theta, delta theta r e theta. We can also derive the form of metric in these coordinates. Like we can compute delta x squared. It will equal to delta r squared plus delta plus r squared sine squared theta delta phi squared plus r squared delta theta squared. For example. But in this one, clear. And if you now substitute it to the definition of gradient, like we can say that the scalar product of a gradient of delta x was gradient of u should be by definition okay, u of x plus delta x plus epsilon delta x. So it equals to like delta r du over dr plus delta phi du over d phi plus delta theta du over d theta. So as a consequence, we can say that so comparing this expression with this and with this, we conclude that gradient of phi is of u is equal to er dru plus e theta 1 over r d theta u plus e phi 1 over r sine of theta d phi u. So we have such formula, and if you now write an action in this case, then so So you should remember the volume element in this spherical coordinates. And who remembers the expression? Like who is dv? In spherical coordinates, in terms of d phi, d theta, dr. Mm-hmm. Dr, d phi, d theta. Yeah, thank you. Uh, so here we write this ut squared minus we should write square of the gradient. So it is ur squared minus minus 1 over r first r squared sine squared theta u phi squared minus 1 over r squared u theta squared. So, and now again, let us compute um, let us compute a variation of the section. So delta s of u equals to the integral without 1/2 dr d phi d theta. So here it is delta u t times r squared sine of theta minus plus delta u mm, r squared sine of theta u r result of the integration by parts plus 1 over sine of theta u phi phi. So it doesn't matter because d phi commutes with sine of theta, so we can rewrite it later. And in the last term, this measure matters because it is theta dependent. So this integration by parts, so delta u. This integration by parts gives delta u times 1 over sine of theta u theta theta derivative. So from here we get that u t t equals to what? We should divide by this r squared sine theta. So it equals to r squared ur r derivative plus oh no wait what did I do? Mm, because it's a mistake, it is sine of theta. Thank you. Oh, it is 1 over r squared here. Oh, let me think. Mm. Yes. Thank you. Yes, I missed this. Mm-hmm. Mm-hmm. So, this piece with u phi, it is 1 over r squared sine squared theta due to u over d. Wait, u phi. Uh, Plus 1 over r squared, 1 over sine theta d theta sine of theta u theta and the tau. So this is the answer for Laplacian and spherical coordinates. So let us rewrite it once again, like just a Laplacian. So this Laplacian equals to Laplacian of u equals to uh,
Putting the variation equal to 0, right? So the integral is
yes, of course.
as usual.
Yes. So just a way to avoid computation of second derivatives by passing on the variation principle. But of course, if you have enough time, you can take this change of variables and compute the second derivatives. It's not very nice computation. But or you can use Mathematica, for example, or some other program to verify this. Yeah. So all this plus n equals to urr plus 2 over r ur. This term can be written in different ways. It doesn't matter. Plus 1 over r squared. And here, if you could write such operator like Laplacian of theta and phi, angular part of this Laplacian, and this angular part is Laplacian of theta and phi is uh, uh, 1 over sine squared of theta uh, of of u phi phi plus 1 over sine theta sine of theta u theta theta. So there is this formula. Uh, so we have some operator in R plus 1 over R squared times some operator in theta and phi. And in 2 dimensions, we had absolutely the same situation. We had some operator in R, and we had in this case, much simpler operator in this single angle variable. So, are there any questions about this? So, and uh, and let us remember what was our original idea. So we wanted to perform separation of variables. Namely, we wanted to choose some basis which would diagonalize some parts of our Laplace operator or wave operator more generally. So we wanted some such basis, but not in the rectangular coordinates. In this case, in the polar coordinates. And so let us try to do this in 2D. So maybe better to say in polar coordinates. So mm, we want to diagonalize this part of Laplacian. So it can be done by the basis of functions which are let us call them psi maybe it is fine. Psi of phi equal to e to the I n phi. So if we choose such basis functions and try to solve, for example, Laplace equation. Laplace of u equals to 0. Then we can say that this u uh, u of r and phi equals to sum over n over integer numbers un of r e to the I n phi. And if we plug this into the Laplacian equation, then we see that an equation satisfied by this components un of r are un with two primes of r plus 1 over r un prime of r minus n squared over r squared un of r equals to 0. And so who knows how to solve such equation? So you see, it is some homogeneous equation. Like if we scale r by some power, it will still be the same. So, so what is the general form of solution of such equations? When it has some name. I don't remember precisely. Maybe Euler type equations. Uh, but
So is the derivative with respect to r of the un s. So should it be en un second of r plus en
who is En? So I'm just taking the sum and plugging into the uh, mm, Laplace equation. So, 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 hmm?
equal 1 mu 5 or 1 over 5.
No, it's too much.
Over r.
Hmm? But how will it help? No, I'm just saying this simple thing. So you see the power of so if you multiply everything by r squared, it will so all derivatives will appear in the combination some r to some power and d over dr to the same power. So it can be written as some polynomial of degree 2 of the operator r dr acting on un of r is equal to 0. So this is essentially a logarithmic derivative in r. So it's a derivative in log r. And so it tells that un of r is r to some power alpha. And if we substitute it here, then we see that it is r that it is alpha squared times r to alpha minus 2 minus n squared r to uh, uh, alpha minus 2 is equal to 0. So alpha equals uh, to plus minus n. So it is clear. Because such equation is the analog of differential equation with constant coefficients, but in a derivative log r. So,
Sorry. Should
hmm?
it be the first derivative is alpha minus 1.
Hmm. But let us just write on this. Probably I can erase something. Maybe this computation. So this equation can be written as r squared u n 2 primes plus r un prime minus n squared un equals to 0. And we can combine these two operators to r dr, then again r dr u minus n squared u equals to 0. So this is uh, d over d log of r squared acting on u minus n squared u equals to 0. And solutions of this equation are u equals to e to n to plus minus n log of r. It equals to r to plus minus n. Is it fine? This is uh, for n different from 0, and for n equals to 0, u can be either 1 or a log of r. Mm, so uh, so we see that now, for example, if you want to solve this problem, uh, so if we solve this problem in the domain r is greater or is less or equal than 1, if we solve this problem in this disk, so then we should remove all the singular terms, and the solution will be un of r phi is equal to sum over integers, some cn cn e to the I n phi r to the absolute value of n. So we can say that it is c0 plus sum from 1 to infinity r e to the I phi to power n cn plus the same sum c minus n r e to minus I phi power n. So do you recognize this expansion? Hmm? So who are these numbers who are these functions in terms of homomorphic and anti-homomorphic coordinates? Because it should be regular at r equals to 0. We should choose that solution which is regular at 0, because we want to write a function which solves this equation in the unit disk. Mm. So are there any questions about this? No? Uh, so mm, uh, So in this case, everything is uh, more or less uh, clear, I think. So we just recovered what we already knew. Mm. Uh, but for example, if you come back to the wave equation which you wanted to study, so uh, uh, let us, for example, solve the following problem: utt minus Laplacian of u equals to 0 with the boundary conditions that uh, so so, um, so it is for r is from 0 to 1. In a sense, we want to solve this wave equation in the disk D. So disk D. And uh, uh, when mm, xy is in the boundary of the disk, then u should be 0. Or we can say that u of t, r, and phi equals to 0 when r is 1. So it is a problem about oscillations of circular membrane. So mm, so membrane with directly boundary conditions. So its boundary is fixed. Mm, so let us look at our equation. So uh, we know that we can diagonalize this part corresponding to angle just by introducing exponentials of a and phi. We can diagonalize in the same way this t part because eigenfunctions of second derivatives are also exponentials but in t. So we can say that this u of t, r, and phi is a combination of some n, probably some other number e to the I omega m t e to the I and phi and times some function u and m of r. And if we plug this into our wave equation, so who can tell what equation will we get from this? What equation will be satisfied by u and m of r?
minus omega n squared.
Mm-hmm. Yeah. What else? Mm-hmm.
Minus 1 over r.
But, oh, times something, right? Right?
Yeah.
Mm-hmm. Mm,
Minus 4 over r. Then open we have a u n
like dr of u and mn. Maybe not as right.
u n w of one derivative. And we can
Right?
minus 1 over squared.
Mm-hmm.
And we get minus n squared.
Mm-hmm. So plus.
But and u n
Mm-hmm. Thank you. So in this in this case, we obtained this equation in R, and what so we can rewrite it once again, or maybe let us write it right here. So well, let us just keep it as is. So. mm, uh, we will study this later, maybe after some lectures. I don't know how fast will go, but this equation is called Bessel equation. So it is a little bit similar to just a usual uh, usual mm, equation like second derivative of function equals to some number, which is solved by sines or cosines. This problem is a little bit similar to this problem in a box, but you see that here there is R dependence, and this will be solved by Bessel functions, which behave like this. So, for example, it's for G0, for n equals to 0. So this solution looks like this. So, solution of this equation is some function which has some non-trivial zeros, and if we want to satisfy this boundary condition, we need to adjust omega m. Well, probably I should have put here. Well, I should have put omega mn because they also depend on n. So we should adjust this omega mn as such that this function is zero on the boundary. And it is a more transcendental than just finding this. Uh, oh, I also forgot to put here some numbers. Kx, ky, and kz. It's more transcendental than to find these functions like sine sine effects or cosine effects, but it is also doable. And the main advantage is that we are able to reduce this complicated multidimensional problem to just a problem in one dimension. So it is not as trivial as it was for the rectangular coordinates, where we could say that Laplacian is just the sum of operators, and each of them is diagonalized separately. Here we see that this eigenvalue of one operator of this actually it's called angular momentum in 2D. So this eigenvalue of the angular momentum enters the radial equation. So and the same will happen in the in 3 dimensions. So in this case, these problems are a little bit similar because you see this structure for the radial part of Laplacian, it is always some UR plus n minus 1 over RUR plus 1 over R squared times angular Laplacian. So in 2D, this angular Laplacian was very simple. It was just a second derivative in phi, and it could be diagonalized by exponentials. But in higher dimensions, it is something less trivial, which we will study the next time. But in any case, it affects a radial equation in a very simple way. It will just give some number, some eigenvalue of this operator. So, and there are actually not so many coordinate systems where this expression of variables can be done. So there are this rectangular coordinates, spherical coordinates, and there are also trivial examples. Ellipsoidal coordinates, and it's generate a case parabolic coordinates, which can be used, for example, to solve at least to do separation of variables in quantum mechanical problem with two Coulomb centers in 3D. Or it can also be done. There is quantum mechanical problem with two Coulomb centers, like two positive charges and which are fixed in some points, and one negative charge which can move in the Coulomb field of these two points. So no, it's a hydrogen molecule, H2 ion. So it is, well, let us write it here. It is this ion. So there is, there are two charges which are fixed at some points, 0. And there is one minus charge which can fly here. So these two are fixed, and this one can move. So a hydrogen atom is just this single charge. So it turns out that this problem with two Coulomb centers can be solved in classical mechanics. So we can find the motion of this charge. But if I switch to quantum mechanics, so if I remember correctly, variables can also be separated, but equations in this separated variables are non-trivial, and not solved in using classical special functions, and this I didn't study this well, but I think it's related to some conformal field theory, Manila equations, and so on. If you go to the quantum problem, so it's something interesting. Uh, okay, are there any questions about this? So this time, so next time, I'm going to tell about this angular part of Laplace in spherical coordinates, and then probably about Bessel equation. Okay, so thanks for your attention. See you next time.